Okay, we can get started a couple of minutes early. Thanks, John. And we'll start with what you've all been waiting for, reliability for quick disconnects, right? So thanks for joining today. My name is Beth. I'm a technologist with CPC, Colder Products Company, out of Minneapolis, Minnesota, in our thermal management business unit. And what we do for the OCP community is we design and develop quick disconnects for single-phase liquid cooling applications. The topic I want to discuss today, reliability, is paramount to ensure consistent operation and performance for data center cooling infrastructure, from the cooling towers on the roof to the CDUs, the rack manifolds, and the quick disconnects that connect to the servers and the cold plates. There's a lot of pieces in the puzzle, but at the root of it, they're all components that need to perform and last and work together. No leaks, no disruptions. Reliability has always been important to mission-critical facilities like data centers, but even more so now with the unprecedented scale at which we're rolling out Liquid for Gen AI. Liquid for compute in and of itself isn't new. CPC has been in the space for about 20 years. We've seen decades of successful deployment in largely on-prem supercompute systems and now scaling into the cloud. A recent example is the Aurora supercomputer system over at Argonne National Lab. When we were working with the engineers at Intel and Cray, now HPE, on designing connections for the manifold that would feed fluid to the individual server blades, as well as connections inside each compute blade that would feed liquid directly to the 16,000 GPUs that are in that system, one of the biggest challenges that I'm proud to say that we collaborated on was developing a predictive model for reliably defining the service life of those connections. That's excellent. How about providing confidence of connections for hundreds of thousands of QDs or millions? That's really the scale and the reality that we're facing today for hyperscale and AI. If you're not familiar with the technology cooling system or TCS loop, secondary loop, we call it a lot of things that I'm sure you've heard throughout the sessions. I'll point you to this graphic that we have in our OCP cold plate guidance document you can find on the project wiki. Highlights a lot of the high-level components that you'll find inside the server. And today I want to focus in on QDs. I've got 10 minutes to talk through reliability considerations for 10 years. Reliability can be interpreted a lot of different ways. I like to think about it as the first derivative of quality. So not only does the quality of our product at time zero matter, but it's really about how does the quality and performance of our product change over time. We often get asked, how long is this QD going to last? What's its mean time to failure? And the response is almost always, it depends. It depends on what? It depends on the application specifics, operating conditions in your specific environment. It depends on other components within the cooling system and the loop. And then it really comes down to how do you know when it's good enough? If you have a O-ring extrude like I have in the video here, or a tube burst or a braze fail at 30 times your operating pressure, is that reliable? If 2 years down the road you have some scale develop, some corrosion that maybe breaks off, flakes off, and works its way into one of your cold plate channels, or a seal on a valve, is that going to be an issue? It really points out the need of having a way that we can connect the dots from inputs at time zero to the extended life with engineering data and logic. So first, starting with addressing that mean time to failure metric, that's pretty straightforward for a lot of applications, but I think in liquid cooling applications, it becomes a little more complex. What failure mode are we benchmarking against? Is it a leak, a drip, a flow impedance, a thermal excursion? There's a lot to unpack there. So what we like to do is break it down into a couple different techniques through physics of failure and predictive modeling. With physics of failure, we can identify and isolate specific failure modes that influence the reliability directly, and then proactively tailor the design, the materials we use to avoid them in the actual application. And then in order to address the time element of that reliability equation, there's really more or less two options. We can set it and forget it, come back in 10 years, and see if your data center is still alive. Or we can leverage some acceleration factors and some predicting aging characteristics to make some assumptions. Okay, isolating the QD, again, as an example of a key component within the TCS, reliability really comes down to two key elements. I'll say material characteristics and then mechanical function and stress over time. On top of that, we layer on to effectively deploy a QD, we want to account for materials and stresses that might be present during the actual operation. So for the purposes of this conversation, breaking the QD down by material, metal alloys, engineered thermoplastics, elastomers, and then characterizing the performance of those materials in the system, we can set a foundation for a broader reliability model that can extend to other components and products that are in that ecosystem. Before we turn on the pump even, there's a lot of things we can do to set ourselves up for success by speccing the right components. So for QDs, obvious things like pressure, temperature, and flow ratings, but also the way that the QD actually interfaces with the rest of the system. Handmate and blindmate connections, we saw a lot of blindmate UQDs out on the floor where you might need to factor in loading from misalignment tolerances, threaded connections where you'll want to make sure that you, I think we were just talking about vibration in the IEC standard, right before this talk, where you have enough torque to seat the part to make it seal, but not so much torque that it's going to induce some undesirable stresses long term. Hose barbs, certainly making sure that you have not only the right tube to the right barb, but checking that that interface can stand other unintended loading scenarios like side load from large bend radii in the connected length. Once you've got your cold plate loop, your manifold, your rack level system set up, it's time to run some tests. And for direct liquid contact, that often comes down to leak testing. The graphic on the upper right is maybe where I'll point your attention there. We've overlain some different leak testing methods with essentially the order of magnitude that leak can detect. And so as we go from right to left, you'll see that some of those test methods start to drop off. They can't reliably measure that resolute of a leak rate. The further left we go, we've also got some things going on under the hood that a lot of my colleagues could probably spend a couple hours explaining to you and talking through the nuances of it, but we're actually moving through different flow regimes. So on the left-hand side, maybe down to 10 to the minus 4, we're still firmly rooted in our viscous laminar flow. When we get past 10 to the negative 6, now it's molecular. I bring that up because it's a nuance in then how we might want to correlate those leak rates with a tracer gas like helium back to a fluid leak. And where it gets tricky is when we do, for example, CPC does helium leak testing on our QDs. We might get a measurement that's 10 to the minus 5th. When I put 100 of those on a manifold, intuitively then we say, okay, now my leak rate is 100 times 10 to the 5th. Or 1 times 10 to the negative 3rd said another way, and according to this, it should be leaking liquid, and that's just not the case. So there's some logic that we need to apply more accurately. Once you've turned on the pump, you're ready to go, you let the system run. How do we ensure that the performance stays consistent? For metal alloys specifically, again, I mentioned metals, thermoplastics, elastomers. For metals, this conversation often centers around corrosion. And there's a tendency to turn to salt spray testing, an ASTM method, where you expose the material, the component, to a highly concentrated salt fog for an extended duration, 24, 72, 96, something we haven't, I guess, as a community aligned on yet, as a way to establish confidence in the materials of construction. There's really a lot of different corrosion mechanisms, though, that we need to take into account for liquid cooling. So the example I want to point to here is galvanic corrosion, where we've got a difference in electrical potential of the materials in the system. So here we have an anodized aluminum connector threaded into a copper or brass fitting with some deionized water flowing through it, and lo and behold, we've created a battery. And the aluminum QD works as a sacrificial anode and has catastrophically failed at the thread. So in order to avoid that, we should certainly be looking at different material interactions and compatibilities. But I guess the point I want to make is if we had done salt spray testing on that single anodized component, we might have had an indication it would last. But clearly there's some nuance when you have interactions in the system. The other thing we always want to keep an eye on is coolant health. I know we had some sessions from our coolant work stream in the cold plate group earlier this morning where we had Keegan and Philip kind of explaining, walking through some test methods and different ways that we can evaluate materials up front. So that's good information to find in the project wiki as well. And then polymers, when we say high-performance engineered polymers, that implies that they come along with some characteristics around thermal and hydrolytic stability, mechanical strength, and compatibility. So in this case, with coolants and other materials in the wetted loop, we can do a number of different front-end stress test methods. And with limited time here, I'll just highlight some around the elastomer methods, as they're usually the critical link in the reliability chain. Sock slit extraction is a useful tool both for thermoplastics and elastomers, where you're essentially forcing extraction of solids, of any additives or compounds that you might have used in your formulation, for an example in this case, an EPDM, and actually extracting those for measurement to get a quantified evaluation of mass or volume change. As far as standardization goes within the community on how we test, how do we define what's acceptable, what's not, again, we can point to our coolant work stream and that IEC standard for a little bit more guidance. Now that we've got everything in the loop defined and our materials are fully characterized, loading scenarios are understood, really for long-term predictive life testing, the conversation really comes about stress management. When I showed that O-ring extrusion on the first slide at 1500 PSI earlier in the deck, how do I know that 5 years, 10 years from now, it's still going to extrude at 1500, or is it going to extrude at a much lower value? This is where we can start to do some really advanced things with taking that material characterization we did earlier and applying it to numerical simulations to account for stresses. I've got a chart on the middle bottom there that highlights some isochronous curves that our engineers developed. Again, back to that example with the Aurora system, specific for that application, where then we could really start to define life relative to stress and strain. So I think that was peak in this example. And if you look at the curves, we can essentially evaluate modulus across those different time ranges. 10-year life, 88,000 hours. I can interpolate between those bottom two lines. So in this case, we were able to design and develop a custom solution for that specific application, a custom barb interface and tubing interface that we would be confident, our customer could be confident that will last for 10 years, and 10 years from now, I'd be happily still holding pressure. Theme of this year's conference was From Ideas to Impact, so I just ran through a bunch of ideas, and hopefully, I guess my ask to you, call to action, is that you come collaborate with us, QD suppliers like CPC, and help those have an impact on the future of liquid cooling. We're ready for you. We've got an army of engineers. I got a couple here with us today that we're ready to help with your questions. In addition, I would point you to our project subcommittee with the cold plate work stream, link to the wiki there, where you can contribute as well. So thank you for attending. I think we maybe have a minute or two for questions, John? Okay. No questions, okay. Not even from you, Emily. Okay, all right, thank you guys, thanks. Oh, Andy.
Hold on. Okay, hi. So I work in liquid cooling, but with immersion cooling, and if you've seen some of the work that's been done, there's a new kind of heat sink called targeted flow. The reason I mention this is that it's quite likely that there'll be some quick disconnects that bring hoses, not with water, to a cold plate with a dielectric liquid, like a hydrocarbon or an ester. I guess that changes that means there's more work to do in the proving of the components in the system. Do you have any comments about reliability or testing that is ongoing or that needs to be done when we go from one fluid type to another fluid type?
Yeah, great example, and that I think kind of ties into the theme or the point I wanted to make about addressing reliability at the material level. So you make a good point about the transition from treated water, PG25 into a dielectric fluid or a refrigerant. We could essentially run the same battery of tests for those materials. Take those dog bones of your polymers, take the slab of your EPDM that you might be using, expose it to that coolant, and then define new characterization, stress limits for that, and then go from there. So it's kind of independent of a component. Good? Yeah. Okay. I hope you had fun at the conference this year. We'll see you again next year. Thanks, guys.